On the 18th of February 2018, an ATR-72 from Iran Aseman Airlines crashed in a mountainside near Yasui Airport in Iran. Poor weather conditions with strong winds, snow and fog hampered the search and rescue efforts, and it took 2 days before the crash site was located. Sadly, all 66 on board had perished. Because of the poor weather conditions, it was speculated that icing conditions were to blame. But the truth is not always what you think. Hi, my name is Magnar Nordahl. I am an airline captain and instructor on ATR aircraft. Thanks to improved training and aircraft systems, the airline industry has an impressive safety record. But sadly, accidents do happen, and while the media is looking for quick answers, the reality is much different. Accidents just don't happen because of a single factor, but are a result of chain of events and mistakes. Very often you can list 4 or more factors that together will result in an accident. And if you could take away just one of those factors, the accident will never happen. Another thing, what many accident reports reveal is that many of the flight crews were composed of a senior captain and a first officer with little experience. What many of those captains failed to do was to ensure a good working environment for the first officers. And that's what we call CRM, Crew Resource Management. It's strange, but in most cases it was the captains who made the wrong decisions, and it was the first officers who tried to do the things right. But they were neglected or overruled by the captains. And because of the steep authority gradient in the cockpit, the first officers were not able to speak freely. This culture is still a problem in some companies around the world. I call this the World War II bomber pilot mentality, because this way of thinking is obsolete. Those captains act like they're flying alone, and they treat the first officers like servants. Apparently, the companies give their pilots CRM training, but do those captains really listen? Do they understand what CRM is? The accident I will review today happened in a mountainous area. Before going into the details, I will talk about some risk factors all pilots should be aware of when flying in the mountains. And they are turbulence, downdraft, Venturi effect, and mountain waves. Just like a boulder is interrupting the flow of a river, a hill or a mountain can create turbulent airflows. This is known as mechanical turbulence and is very common. As a general rule of thumb, when the wind velocity is 50 knots or more, you should expect turbulence on the downwind side of a mountain, or a hill, or a building. The extent of the turbulence depends greatly on the stability of the air. Severe turbulence can result in strong downdrafts and loss of control. However, there are very few reports of airliners breaking apart in turbulence. The last time this happened was in 1966, when a Boeing 707, operated by British Overseas Airways Corporation, BOAC, encountered severe turbulence near Mount Fuji in Japan. The airplane was downwind of the mountain and 4,000 feet higher than the summit, when a very strong sideways load caused the tail fin to collapse. All 124 on board died. Later that day, a US Navy A-4 Skyhawk, which took part in the search and rescue efforts, flew into the same turbulence and encountered load fluctuations between -4 and +9 G. The pilot survived because military airplanes are built much stronger than airliners. Downdrafts are associated with mountains and wind. Here is an example. Let's assume that a wind of 20 knots is blowing down a mountainside with a slope of 30 degrees. The vertical component is then 10 knots. 10 knots are 10 nautical miles per hour, which equals about 60,000 feet per hour, or about 1,000 feet per minute. This can easily overpower the climb capability of an aircraft at high altitudes. When air is flowing over a mountain ridge, it is compressed. This causes the velocity of the air to increase, and as a result, the static pressure decreases. As a consequence, the altimeter indicates a higher altitude than you really are. The altimeter error can be several hundred feet, and in extreme cases, more than 1,000 feet. When air is flowing perpendicular to a mountain ridge with a velocity in excess of 15 to 20 knots, it can start to oscillate, creating waves that can extend hundreds of kilometers behind the mountain. For such waves to form, there must be a stable air mass over the mountain with less stable air above and below. The vertical speed of the updrafts and downdrafts can exceed 3,000 feet per minute. If there is enough moisture, there will be formed lenticular clouds, where you can find moderate to severe icing. In addition, there can be severe turbulence below the crests, often identified by rotoclouds. In 1955, a B-29 flew through mountain waves over Owens Valley and Sierra Nevada in the western part of the United States. On this figure, the aircraft crossed from right to left at 20,000 feet. The headwind was between 50 and 60 knots, and the true airspeed was about 220 knots. The power was not changed during the encounter. Here, the aircraft hit a downdraft, and the vertical speed was minus 1,000 feet per minute, while the airspeed decreased to 142 knots, as the crew tried to maintain altitude. The altitude loss was 1,200 feet, and the aircraft came close to the stall speed. Then, the aircraft hit an updraft that caused the aircraft to gain 4,400 feet. Vertical speed reached plus 1,600 feet per minute, and true airspeed increased to 262 knots. Then, the aircraft hit a second downdraft. In this case, airspeed was not ready for altitude, and they lost a total of 6,800 feet before recovering. This clearly shows the power of mountain waves. Glider pilots can utilize mountain waves to reach very high altitudes. The ultimate altitude record was set in 2018 with this glider, the Airbus Pelan II, with 76,124 feet. That's higher than the service ceiling of the U-2 spy plane. I have flown gliders, but not that high. Most of my gliding experience is in hang gliders. Like the birds, we can utilize upwinds along mountain ridges and thermals, which are columns of hot air rising from the ground. This enables us to fly for many hours and long distances. However, mountain waves are not our domain. The wind is just too strong. I have been flying for more than 40 years and experienced one emergency. That happened in a hang glider. I was soaring along a hillside when the wind force suddenly increased. There was a mountain wave behind a mountain 50 kilometers away, and this mountain wave suddenly changed position and altitude and caught me. I was not able to fly forward and out of this hill, but was caught by turbulence at low altitude, and suddenly I was flying in the opposite direction at a very high ground speed, very low above a forest. There wasn't room to turn back into the wind. I had an emergency chute and decided this was the time to use it. The emergency chute is attached to the wing, and it deployed as it should. A few seconds later, I landed on the top of a small tree. After climbing down to safety, I pulled the wing down. It was winter, the snow was steep, so what could I do? But thankfully, there was a ski trail nearby, and a skier passed by. He was a bit curious about what I was doing there, so I told him the situation. He gave me a map, and it showed me the direction to a car park. And there I met a man who gave me a lift back to the civilization. And thankfully, I met my friends before they triggered a search and rescue operation. Because of the risks associated with mountain flying, the Instrument Flight Rules, IFR, require you to fly at least 600 meters or 1968 feet above the highest obstacles in mountainous areas, which are defined as having an elevation of more than 1850 meters or about 6,000 feet. ICAO uses meters as primary unit of measure. It is important to remember that MSA, minimum safe altitude, which is inside a radius of 25 nautical miles from an airport, only gives 300 meters or 984 feet obstacle clearance. This may not be safe enough when you're flying IFR over mountains. Iran Aseman Airlines Flight 3704 was a scheduled flight from Tehran Mehrabad Airport to Yasoi Airport. It was served by an ATR 72 with the registration Echo Papa Alpha Tango Sierra. There were 66 people on board, including the crew. Mehrabad Airport is the second largest airport in Tehran and is used for domestic traffic. The flight to Yasoi will take 1 hour and 40 minutes. Yasoi Airport is located in a mountainous area in southwestern Iran. Airport elevation is 5,940 feet, or roughly 6,000, and near the airport, towards northeast, there is a mountain range named Zagros Mountains. The highest peak is 14,465 feet above mean sea level. When you fly from Tehran to Yasoi, you have to cross over those mountains. The minimum altitude on the airway is flight level 170 or 17,000 feet. If you elect to fly outside the airway, you will have to respect grid Mura, which is 16,900 feet. This gives you 600 meters obstacle clearance. Inside a radius of 25 nautical miles around the airport, the MSA is 15,500 feet. But this gives only 300 meters or 984 feet obstacle clearance. The operations manual allowed the crew to descend to this altitude inside 25 nautical miles from the airport. At the time of the accident, the only instrument approach procedure available was an NDB approach for circling. It can be flown with a GNSS or GPS, but you must respect the indication from the NDB. The procedure has a MDA, minimum descent altitude, of 10,100 feet. This is 4,160 feet above the airport. But when there is a cumulonimbus, CB, in the area, the operation manual requires a cloud ceiling of 11,000 feet above the airport, or 17,000 feet above main sea level. That would allow for a visual approach. The reason is that the CB can create electrical disturbance to the signal from the NDB, which will make it unsafe to use. Normally, when you have a thunderstorm, that means a CB, the needle in the aircraft will point towards the center of the cloud. And that is not so good, right? So because of this, Yasoi Airport is classified as a Category C aerodrome, which means the flight crew must undergo special training. And both crew members were fully qualified for this flight. The captain was 62 years. He had almost 18,000 hours total time, whereof 12,500 hours in ATR 72. He was also the training pilot of the company and examiner. In the last 3 months before the accident, he had made 2 flights to Yasoi. The first officer was 36 years. He had 1880 hours total, whereof nearly 200 hours in ATIA 72. As the accident report later stated, there was a steep authority gradient between the pilots, and this prevented effective communication between them. On this flight, it was the first officer who was pilot flying, and the captain was pilot monitoring. There was no tough or other weather forecast for Yasui. Therefore, the crew needed two alternate airports. In this case, Esfahan and Shiraz were selected as alternate. Before departure, the crew received a weather report, or METAR, for Yasui. Wind calm, visibility more than 10 kilometers, few clouds 4,000 feet, broken clouds 9,000 feet, temperature +6, dew point -0, QNH 1022. However, the regional area forecast showed a degrading situation with the possibility of CB with thunderstorm, rain and hail. There were also strong winds from the west at cruising altitudes. Therefore, the crew should expect the weather to be below operational minima when they arrive at Yasui. Remember, a CB near the airport requires 11,000 feet ceiling above the airport. But they could still depart and get weather updates on the way and then make the decision whether to continue or divert to one of the alternate airports. The aircraft departed Tehran Mehrabad Airport at 08:05 local time, and they climbed to flight level 210, 21,000 feet, which was the cruise level. At 09:19, they passed Obtuk's waypoint, which is 44 nautical miles from Yasui. At that time, they received the following weather update for Yasui. Wind from 90 degrees at 4 knots, visibility more than 10 kilometers, few CB at 3,500 feet, scattered clouds 4,000 feet, overcast clouds 9,000 feet, temperature 14, dew point -1, QNH 1022. The presence of CB should have prompted the crew to divert to an alternate airport, as they will need a cloud ceiling of 11,000 feet above the airport. But this was not discussed by the crew. The flight was then cleared to flight level 170, and they started to descend. They contacted Yasui Tower, which informed them that the sky was cleared in approach area. The captain assumed that they would break clear of the clouds between 14,500 and 15,000 feet, and then be visual with the airport. After contacting Yasui Tower, they continued to descend onto 15,000 feet. As they descended, they passed through an updraft and then a downdraft. The pilot flying adjusted engine power to counteract this. Despite that had 50 to 60 knots headwind and experienced those disturbances while flying towards a mountain range, the crew didn't discuss the possibility of mountain waves. It was not in their mind. Just as they leveled off at 15,000 feet, they entered a strong updraft. The power was reduced to idle and the airspeed increased to 205 knots. Then, a minute later, they encountered a strong downdraft. The speed started to bleed off and the power levers were set in the notch, which gave maximum cruise power. However, this was not sufficient to maintain altitude and a safe airspeed at the same time. The pitch increased to 15 degrees up and the speed decreased to 130 knots. The first officer asked whether they should set flap 15, but he was ignored by the captain. Then, the first officer asked whether they should descend, and the captain instructed him to descend to 14,000 feet. The speed continued to decrease, and at 170 knots, the stall warning activated. This caused the autopilot to disconnect. The first officer lowered the nose, increased the power to maximum cruise power again, and asked for flap 15. But instead, the captain told him to engage the autopilot. The autopilot was engaged and then altitude hold mode was engaged. A few seconds later, while descending through 14,000 feet with a vertical descent rate of nearly 4,000 feet per minute, the ground proximity warning system triggered a series of terrain alerts.
Terrain ahead. Terrain ahead. Terrain ahead. Pull up. Terrain ahead. Pull up. Terrain ahead. Pull up. Terrain. Pull up. Pull up. Pull up.
Shortly after, the aircraft impacted a mountainside about 300 feet below the top of the ridge. The time was 09:31. The accident investigation took 2 years. Meanwhile, some aviation experts had already concluded that the aircraft had come down due to icing. Yes, it was icing, but analysis of the flight data recorder revealed that icing did not affect the performance or handling qualities of the aircraft. Furthermore, the aircraft was fully operational with no defects. The investigation revealed that the following factors resulted in the accident. 1. They continued to use Saudi Airport despite the weather conditions were below operating minima, as described in the operations manual. 2. They descended below MSA. 3. Poor CRM, which in turn led to number 4, improper stall recovery, and 5. Improper use of the autopilot. If they had deviated to one of the alternate airports, the accident would never happened. If they had leveled off at 15,500 feet, they could have avoided the accident. If the stall recovery had been executed in accordance with the published procedures, they could have avoided the accident. Just setting flap 15 would have made a big difference, and if they had set maximum continuous power, they would have 22% more power than they actually had. In an emergency, you can increase power to even more. When we practice wind shear in the simulator, we move the power levers all the way to the wall, which gives another 15% power. Finally, engaging the autopilot just after a stall warning in a steep descent made things even worse, because the autopilot needs time to correct the flight path, time they didn't have. They were only 300 feet from clearing the mountain. If they had made only 4 of those 5 errors, the accident might have been avoided. As I said earlier, in many accidents, the captain was experienced with high seniority, and the first officer was inexperienced. This can often lead to a steep authority gradient, which reduces the safety of the flight. On this flight, the first officer did many things right. For example, he did a very detailed approach briefing, but according to the voice data recorder, he did not get any response from the captain. And when the first officer asked for flap 15, he was ignored 2 times. Neither did the captain ensure that maximum continuous power was set. And that's not all. It was the captain who initiated the descent below MSA. And it was the captain who ordered the autopilot to be engaged just after the stall warning. It's sad, but it was the experienced captain who messed it up. Future airliners might have a single pilot, a captain, and a dog. The job of the dog will be to bite the captain if the captain touches anything. That's a joke, of course, but one thing is clear. Something has to be done with those captains with the World War II bomber pilot mentality. Can they change their attitude? Or do we have to wait for them to retire before commercial aviation will become even safer than it already is? What do you think? Please leave your comments below. And that's all I have for this time. Thank you for watching. Have a wonderful day and happy landing.